In the last video, we worked at maximizing and minimizing the value of a multivariable function subject to some constraint. However, if we are working with a function of three variables, it is possible to have more than one constraint. Basically, if we have one constraint, what we are trying to do is optimize our function over all points on a particular surface, on a particular, basically a level surface. But if we have two constraints, those two constraints are two surfaces, and they will intersect in some sort of curve. And so, well, hopefully in some sort of curve. But basically what we're trying to do is optimize our function over that curve rather than a surface. So let's, for instance, take two constraints. We're going to actually call these g and h, the functions that are going to be involved. G is going to be x squared plus y squared plus z squared equals 9. Normally it'd just be written as this part over here without the g equals, but we do want to give a name to these eventually, like we did in the last video. For h, I'm going to say x plus y plus z equals 1. If we go ahead and plot those constraints, so x squared plus y squared plus z squared equals 9 is going to be a sphere with radius 3. Then x plus y plus z equals 1 is a plane that cuts through that sphere. Actually, I forgot that I changed this. I wanted this to equal to 0 instead. That'll make things a little bit easier to work with when I'm just trying to set things up. It wouldn't be impossible to solve it otherwise, but I do want to make this as easy as we can from now. But the point here is that we have a plane intersecting the sphere is what our two constraints mean, and their intersection is a certain, well, it's writing as a conic, but it's a circle. I'm going to go ahead and make that a little, I'm going to color it black and make it thicker so we can actually see what's going on. But we have this circle, and we're just looking at points on that circle and asking what is the maximum value of a particular function. Now, I haven't given you a function yet, but let's say we had a function f of x, y, z is equal to, say, x squared plus yz. X squared plus yz. We want to be able to maximize that function, maximize or minimize. In fact, we're guaranteed that there is going to be a maximum and a minimum on this set, because this is technically a closed set in the plane, or not in the plane, in three-dimensional space. It is closed. Its boundary is itself. It's just that curve. It's the circle. Its boundary is itself, and it doesn't go off to infinity. So our extreme value theorem actually does apply here. So we are guaranteed that there is going to be a maximum and a minimum value. We want to know what that maximum and minimum value is. Now we're going to go ahead and try to plot various level surfaces of this thing here. That is going to make me have to kind of solve things. GeoGebra won't really like it if I put in x squared plus yz equals k. It won't really work too well. So I'm going to solve that so that z equals an equation in terms of x and y, and it will plot those various surfaces. Of course, I do need to make a slider first. So I have a k value that I can put in. So I have a k value. I can plot various level surfaces that look like, say, f of xy is equal to k minus x squared divided by y. If I set z equals that and move things around, that's the same as the equation x squared plus yz equals k. So that will give us various level surfaces. And let's actually change the color of that. I want it to be a different color than my sphere. Make it a darker blue. Okay. So for the value of k equals negative 0.1, this is the level surface for that function of 3 variables. Now, of course, there are values both that are on the circle. So we're really looking at where the sphere and the plane intersect with at the same point as our level surface. So we have a point here, we have a point here, and a couple points down here as well. But if I move my slider, those aren't really going to be. That's not a maximum or a minimum point. Now let's go ahead and see how far we can go with this. If we make our k as small as we can and still actually have a point where this level surface actually intersects the sphere, or not the sphere. Well, we're not looking at we're looking at where it hits the circle technically, because that's what we're trying to maximize over. The sphere is just kind of in here. In fact, we could take out the plane and sphere and just look at the circle. Kind of shaded in the middle, but oh well. We just look at the circle and move this around. We see that the smallest we can get and actually touch it is maybe around negative 0.44. Something like that. I don't know. It's kind of hard to get exactly where it is. Maybe it's negative 0.45. That's as low as we can go and still have the surface touch our circle. And you can kind of tell that we still have the same idea that we had before, where this surface does seem to just be tangent to the circle at that point, at those points, when k equals negative about 4.5. If we go the other way and see how big can we get and still actually intersect that circle. If we go out to, say, 8.7, it doesn't actually touch anymore. It's too far out. If we move this down a little bit, I'm kind of looking here at whether or not I'm seeing it all dashed there or not. About 7.7, I lose that solid line that was outside our surface. So I'm going to say around 7.7 or maybe 7.6, somewhere in there. Actually probably see a little bit of gaps there, so maybe closer to 7.6 or something like that. Of course, I'm just eyeballing this. It's not really as exact as actually solving it, and we're not going to be doing this in general, but at least get an idea of what's going on. But the point here is at my highest point. Let's just say it's a 7.5 for just to settle on something. We can kind of tell that our surface is again just going to be tangent to that circle. So we're just kind of we're looking for where our level surfaces are tangent to our curve. But unfortunately, because we're not just dealing with the curve directly, we're dealing with the constraints that we had. We can't really ignore the fact that we're really working with the sphere and the plane. And how is this level surface going to be related to the sphere and the plane? Well, down here at negative 4.5, we actually can see that our level surface is actually going to be tangent to the sphere. That's really nice. But when we're up at the other end at 7.5, even though our level surface was tangent to the circle, it's not tangent to the sphere. It's actually kind of cuts into the sphere on both sides. And in fact, at neither end were we ever tangent to the plane. So we actually are not in a situation where we're just trying to find where the level surfaces of our f value intersect, or well, are tangent to our constraints. That's not what we're going to be doing. Well, let's go ahead and We'll ignore the level surfaces for now and just focus on trying to get an idea of how to look at normal vectors to our curve and surface, because that's going to help us out. Let's go ahead and plot a particular point. I'm going to pick the point 0, -3 square root 2, and 3 square root 2. What did I do there? Oh, right. I misread my notes. So this is supposed to be -3 over square root 2 and 3 over square root 2. There we go. Now we have a point A that is on our circle. It satisfies both of our constraints. If we look at, so we're looking at the point 0, -3 over root 2, 3 over root 2. If we look at the gradients of g and h, gradient of g, just differentiating this with respect to x, y, and z, so we have 2x, 2y, 2z. At this particular point, I don't know, should recall that a, so I'm just going to call it a as well, just so I don't have to write that again. But when I plug these values into here, of course my first component is 0. My second component, the 2 over square root 2, is going to put a square root 2 on the top. Same thing over here. If we look at the gradient of h, this one's actually pretty nice because this turns into a 1, 1, 1. And in fact, I don't even have to rewrite that. That's the gradient of h at a as well. All that's really saying is that when I'm dealing with this plane, the normal vector at one point is going to be constant over that entire plane. We just haven't have the same vector pointing out the same direction all the time. If I go ahead and plot the vector that starts at a, and I finish it up with I add 0, -3 square root 2, 3 square root 2. That is a vector that points out, and this is supposed to be normal to the sphere. It's pretty easy to see that that's the case. It's definitely not normal to the plane, but we didn't expect it to be. We'll also take the vector that starts at a and goes out by 1, 1, 1. A different length, but it is a vector that starts at the point A and is normal to the plane. Well, it turns out every vector that is normal to this curve, every vector that is perpendicular to this curve, is going to be in the plane that is spanned by those two vectors. Let me go ahead and actually put in that plane, which doesn't let me put in planes based off of two vectors, but I can use those vectors to generate lines, and then use those lines to generate the plane. Let me take out not show those lines. So we have a plane that is determined by those two vectors, and every vector that starts at A ends up at some point. Every vector that starts at A and is perpendicular to the circle ends at some point in that plane. And so we're asking, can we find a vector that's in this plane somewhere that is also perpendicular, is normal to our level surface that we had before? If we bring that back up again, of course, I didn't really pick a point where that was going to be one of the maximum and minimums of the level surface, but you can imagine what we're trying to do is figure out a point over here where that normal to it would stick into that plane determined by the gradients, the normals to these other constraint equations. Can we find a point where the normal to this level surface was in that plane? Well, how do we determine whether things are in a plane if we're given by two vectors? Well, we look at what we call a linear combination. We're basically trying to see, is there some combination of gradient of g and gradient of h So gradient of g and gradient of h, and any scalar multiple of gradient of g, probably use a lambda there. And for gradient of h, any multiple of that, we'll use a Greek letter mu. And then any sum of those will also be in that plane. In fact, anything of this form for some lambda or mu is going to be in that plane, and any point in the plane is going to be in that form. So that means we end up wanting this equation. We want that the gradient of f at that point to be some lambda times the gradient of g at that same point, plus some mu times the gradient of h at that point. Lambda and mu are going to be our Lagrange multipliers. We actually have two of them this time. And that is going to basically introduce a new variable. Instead of having lambda as a variable, we have lambda and mu. But we also will have an extra constraint, and that will make sure that we have the same number of equations as variables when we're solving our problems. Now, one thing I will note, and the book kind of doesn't write this out like it did the previous one. You kind of have to read through the entire paragraph that they spent explaining all this, which I don't know if that really explained everything to you, but the main things that we have to worry about here is we needed the gradient of g to not be 0 at the point in order for our single constraint problems. Here we need the gradient of g and the gradient of h to not be 0, because we need our surfaces to actually be rather smooth, but we also need those gradients to not be parallel. So we have two different gradients and we need them to not be parallel, or else we're dealing with two constraint surfaces that are actually just tangent to each other. And that can cause a few issues. We're not going to look at any places where that's going to happen, but just be aware that there are some restrictions here. But let's just kind of roll with it and see what happens. Let's work on problem 17. We're trying to find any extreme values, any maximums or minimums, if we can. We have a function, x plus y plus z, fairly nice function there. We have two constraints, x squared plus z squared equals 2, and x plus y equals 1. If we go ahead and plot those, just to get an idea of what our constraint really is, technically we don't have to do this, but we might as well. So x squared plus z squared is equal to 2. That's a cylinder. Now, the cylinder might actually be an issue for us if we were doing a single constraint problem, because it does go off to infinity in two directions, and so we wouldn't be guaranteed to have an actual maximum or minimum. But when we put in our other constraint of x plus y equals 1, we see that the intersection this is an ellipse. If we intersect these things, and actually make that conic not the same color as the cylinder, and have a thicker line so we can actually see what's going on, we have this ellipse just kind of sitting there. That ellipse doesn't go off to infinity, and so our constraint actually is bounded. And so we will actually end up with an actual result here. We will end up with a guaranteed maximum or minimum. But we're just going to take the gradients of all these functions and see what happens. So this first one I'm going to call g, the second one I'm going to call h. I'm not going to write that out just to kind of save us on some space here. But hopefully you've seen that enough that we can just roll with it. The gradient of f, we're just differentiating this with respect to x, then y, then z. The derivative with respect to x is 1. Then we get a 1 and another 1. Fairly nice thing there. Gradient of g. So here we have x squared plus no y's plus z squares. So the derivative with respect to x is 2x. Derivative with respect to y is just going to be 0. And derivative with respect to z is 2z. Finally, the gradient of h. Well, this one's actually pretty similar to f, except we don't have a z in there. So we actually get a 1, 1, and 0. We want to satisfy this equation here. So we're going to introduce lambda and mu that are going to multiply the gradient of g and gradient of h, and then we're just going to turn this into three equations. We're going to have the first component of f is equal to the first component of g times lambda, so 2 lambda x, plus the first component of h times mu, so we end up with it, just plus mu there. Do the same thing, we have 1 is equal to, this time, lambda times 0, plus mu times 1. And then we have 1 is equal to 2z times lambda. And this time it's plus mu times 0. So we have three equations so far with 5 different variables. Of course, we do have our two constraints that we need to put in here. We have x squared plus z squared equals 2, and we have x plus y is equal to 1. There's a system of 5 equations with 5 variables. Now, one thing that's very nice about this one right now, and we shouldn't expect this in general, we actually already identified what mu is equal to. Mu has to equal 1. That's guaranteed already. In fact, we can modify our first equation here by plugging in 1, and then just canceling out the 1's from both sides. We actually have 2 lambda x is equal to 0. So we've actually already reduced it down to a system of 4 equations with 4 variables. Now what we can see already from here is that either lambda equals 0 or x equals 0. If we were to set, I'm going to even write this over here. If lambda equals 0, what would that cause? That would cause this equation here, this 1 equals 2 times 0 times z, to not be true. So we can't have lambda equals 0. That's just not possible. This is case 1, sorry. Case 2, it's the one that has to be true, is that lambda is not 0, and since lambda times x has to equal 0, that means that x has to be 0. So we already know one of our variables, so we already knew what mu was, we already identified what x is. This one actually works out pretty smoothly, but you shouldn't expect that always to be true. It's mostly just because we're dealing with we're dealing with a plane and we're dealing with a linear function. So those are very nice functions to work with. That's why things are working out as smoothly as they are. Okay, so x equals 0. Actually, we can go ahead and just immediately plug that into our fourth and fifth equations, our constraints. If x equals 0, that means that z squared equals 2. And it also means that y equals 1, which actually already identifies what y is. But then z has two possibilities, plus or minus square root 2. Again, we didn't identify what lambda is, but we don't necessarily need it. You could figure that out from 1 equals 2 lambda x, or 2 lambda z if you want to. So we have 2 points. We have 0, 1 square root 2, and we have 0, 1 negative square root 2. I'm just going to go ahead and not bother writing out a full chart for these. I'll just plug those into my function. So at 0, 1 square root 2, we just add those together. We have 1 plus square root 2, which is approximately 2.414. Then we add these together, we have 1 minus square root 2, which is approximately negative 0.414. If we go ahead and plot those points on our graph here, we have 0, 1 square root 2, and we have 0, 1 negative square root 2. Those turn out to be the points at the top and bottom of this ellipse. Top meaning it's actually the highest z values and lowest z value on the ellipse. But we can see that the x plus y plus z is as biggest up here, and it gets smaller as it goes down to here. So kind of interesting. I wasn't sure if we'd have time for this example, but I did want to get to it if we did. This is going to be another long video like we had in the last one, and we will have another example after this one. Hopefully this won't take too long. But we have another function. This actually is a very nice function. It's just the z value. But we have constraints, this x squared plus y squared equals z squared. And then we have x plus y plus z equals 24. So we have one of those is a nice plane. So again, I want to give you an idea of what this looks like. So x squared plus y squared plus z, x squared plus y squared minus z squared equals 0. This is a cone. If we graph x plus y plus z equals 24, we get a plane. It doesn't look like it hits it. We actually need to zoom out quite a bit before we can really see what's going on here. Okay, that might be far enough. So what you can see here is that we have a plane that intersects this cone. And if you remember anything about conics, when a plane intersects both the top and bottom parts of the cone, we always have, as long as it doesn't pass through the vertex, as long as it doesn't hit the origin there, we automatically have a hyperbola. This curve is a hyperbola. It has two pieces. It has one up here, one down here, and then it's not bounded. That's kind of an issue in this problem. We do not have a bounded curve. So maybe, well, actually, we can even already discuss what's going to happen here. So remember, our function that we're trying to maximize or minimize is the z value. If we look at this curve, it definitely just goes off to infinity in a direction where the z keeps increasing. And it, in fact, does the same thing with z is decreasing. There actually is not going to be a maximum or minimum of this function. But we're going to go ahead and roll with it anyways, because we only got that information from graphing it. And in general, we won't, graphing it, well, I guess with GeoGebra we can graph a lot of things, but sometimes graphs can be misleading if we don't know what we're looking for and stuff like that. And GeoGebra does struggle to graph some surfaces, so we may not be able to get the graph in a more general situation. So let's see what might come out of this if we use our technique. Of course, we're going to go ahead and take our gradients. This first one's going to, well, I should note here that g of x, y, z, I need to move the z squared over to the other side. So actually I'm going to call this x squared plus y squared minus z squared, and that g needs to equal 0. H, of course, we don't really have to do anything here. This is going to be x plus y plus z, and that needs to equal 24. But the gradient of f, since there's no x's or y's, we have 0, 0, and then we just get a 1 for the third one. That's actually pretty nice. Gradient of g, this time we're going to have a 2x, 2y, and negative 2z. And finally, the gradient of h is going to be a 1, 1, 1. Again, this gives us 5 equations. Well, 3 of them come from our gradients. We have the first component here, 0 is equal to lambda times the first component of g, plus mu times the first component of h. We again have 0 equals 2 lambda y plus mu. And we have 1 is equal to negative 2 lambda z plus another mu. And we attach that to our two constraints. X squared plus y squared equals z squared. And x plus y plus z equals 24. My first thought is that if I look at these first two equations, these both equal 0, so they're also equal to each other. And in fact, the plus mu here I can cancel out. We really well, I go ahead and subtract mu and divide by 2, so I'll have lambda x equals lambda y. Of course, there are two possibilities here. Lambda could be 0, in which case this would definitely be true. But if lambda were equal to 0, what would that do? That would, well, from our first two equations here, if lambda equals 0, then 2 lambda x equals 0, so mu would have to equal 0. But if I put 0 in here, then negative 2 lambda z would be 0, and mu would have to equal 1. So lambda equaling 0 would cause a problem. It would give us two contradictory values for mu. So lambda is not going to equal 0. So if lambda is not 0, we can divide by lambda and just get that x equals y. That's pretty nice. We can go ahead and plug that into our constraints. So our first constraint becomes just 2 copies of x squared is equal to z squared. And our second constraint is 2 copies of x plus z is equal to 24. If we go ahead and, well, let's actually just go ahead and solve this one for z. Z is either plus or minus x times the square root of 2. I just square root everything, but I have to deal with that plus or minus. We can go ahead and plug that into here. So 2x plus or minus x times square root 2 is equal to 24. Or in other words, if we divide 24 by 2 plus or minus square root 2, we have our values for x. Now there's two different values here, depending on whether we pick plus or minus, and that's going to give us two different points on the curve that will be important points. Our first point is 24 over 2 plus square root 2. Of course, that's our x value, and our y is equal to x, so it's the same thing for our y value. Z is going to be, well, if we have a plus sign here, it's because we had a plus sign here. So we get to multiply this x by a positive square root 2 to get our z value. So we have 24 square root 2 over 2 plus square root 2. On the other hand, we have 24 over 2 minus square root 2. Same value for y. And if we had a minus sign here, it's because we had a minus sign here. So this time we get it multiplied by a negative square root 2. So kind of complicated expressions there. Again, these aren't necessarily, well, we know these aren't maximum and minimum points because we know that the function does go off to positive and negative infinity on this curve. But these actually turn out to be important points. So if I go ahead and plot these, and I'm going to kind of make it easier on myself, since everything on my first point is going to have a factor of 24 over 2 plus square root 2, rather than having to do that multiple times, I'm going to use the fact that GeoGebra can work with vector multiplication, scalar multiplication, and just take the 1 square root 2 times 24 over square root 2. That gives me a point that you can kind of see here. Then I do the same thing. We have 1 negative square root 2 times 24 over 2 minus square root 2. And that gives me the point here. So notice, while we don't actually get the maximum and minimum values of the function, we did actually get some important points. These are the vertices of this hyperbola. And you could say that, say this point A here is actually a local minimum for the function f. So there, around this point, there are no values of the function f on the curve that are lower. It is the lowest z value for this upper part. In fact, we could have actually even put in an extra condition on our constraints where we're only considering z values that are, or points on this intersection that have z greater than 0. In which case, this would actually be the minimum. Same thing over here. You could say that b is a local maximum. So we actually did identify something that is kind of significant for the particular function with regards to this curve, even though you might not say that it is the maximum or minimum that we would have been looking for, just because this doesn't have an absolute maximum minimum on the whole curve. And of course, that was only because we were able to go off to infinity. If we had something that was bounded, like we had in all the other examples we've looked at in this section, then we would have guaranteed found an actual maximum or minimum for this particular problem. Now, this is a little bit different from the last two. We're going to look back at our original goal. We were trying to find the absolute maximum and minimum values of a function over a region. This was from our last section. And there we were able to find critical points on the interior as possible maximum and minimum points, but we had an issue where the boundary may not be easy to work with. So what we're going to do is use Lagrange multipliers to handle the boundary part. So this is really kind of a problem from the last section, but now we have additional tools to work with it. So we're trying to maximize this function, x squared plus y squared plus 4x minus 4y, but we're on the inside or boundary of this circle, x squared plus y squared is less than or equal to 9. So we can go ahead and draw that. Not going to use GeoGebra this time. We are just dealing with a circle of radius 3, and we're trying to look at anything in that closed disk. Could be on the boundary, could be on the inside, not sure yet. But we have two parts. We can look for critical points in the interior, and then we can look at using Lagrange multipliers to find the extreme values on the boundary. Let's start with the interior. Of course, we're going to use the techniques from the last section, where we look for any critical points by taking the partial derivatives and setting them equal to 0. So partial derivative this with respect to x, that's 2x plus 4. Partial derivative with respect to y, that's 2y minus 4. We want to set those equal to 0. Of course, these are fairly easy to solve because, well, the first one immediately gives us our x value of -2, and the second one immediately gives us our y value of 2. So we have a point -2, 2 that is a critical point for this function. Now, one thing we might want to do here is check, is that inside this domain? Is that actually somewhere in this circle? Well, x squared is 4, y squared is 4. If we add those together, we get 8. 8 is less than or equal to 9, so it is in the circle. It's actually pretty close to our boundary. So -2, +2, so we're actually getting a point around here-ish. So that's a possible point. We're going to save that point for later. Since we're not going to use the second derivative test here. We're just going to compare it to the values that we get from Lagrange multipliers. On the boundary, we want to take our gradient of f equal lambda times the gradient of g. We actually have the gradient of f already. The gradient of f just comes from these partial derivatives, so it's just 2x plus 4, comma 2y minus 4. Let's actually go ahead and write that out. Our gradient of g, this time our g is x squared plus y squared, because our constraint here is actually the boundary x squared plus y squared equals 9. So our gradient of g is 2x, comma 2y. And so we have 2x plus 4 needs to equal 2x times lambda. 2y minus 4 needs to equal 2y times lambda. And then, of course, we have our constraint that we need to throw in there. And we need to solve this system of equations. Now, if we move stuff around, I'm going to go ahead and take both these first two equations. Well, actually, let's just start with actually, no, we're going to use both of them. I'm going to take these two equations. I'm going to move everything with x's and or y's to the other side. I'm going to move the constants to the other side. So the first one, well, actually, before I even do that, let's just divide those equations by 2. So this first equation becomes x plus 2 equals lambda x, which then we can move the lambda x over to the other side, and that's going to equal a negative 2x. So let's instead move this x over to the other side and make it lambda x minus x is equal to 2. Or in other words, if we factor out the x, we have x times lambda minus 1 is equal to 2. On this one, again, we divide by 2. We have y minus 2 is equal to lambda y. Moving the y over to the other side, we have a lambda y minus y is equal to negative 2 this time. We can factor out the y, so we get y times lambda minus 1 is equal to negative 2. Now, why is that helpful? And you might try something else and not get to this point, because this is what I found by playing around with it. This might not be the best way to tackle it, but that's just what I found. But the point here is, if I were to set lambda equal to 1, this couldn't be true, because we have 0 equals 2 or negative 2. So lambda is not going to equal 1, but what I can see from here is that x times lambda minus 1 is the negative. These are negatives of each other. These two things, we have x times lambda minus 1 is the negative of y times lambda minus 1. Or actually, let me swap x and y here. And I already mentioned that lambda can't be 1, so lambda minus 1 is not 0. So this equation actually means that y has to be negative x. Can you see that? Once I have y equals negative x, and I have x squared plus y squared equals 9, I can go ahead and replace my y with negative x, which just gives me, the square gets rid of the minus sign. Or in other words, x is going to be the square root, or plus or minus the square root of 9 over 2, or we can just write that as plus or minus 3 over root 2. Of course, y is the negative of that, so we end up with 2 points. We end up with 3 over root 2, and then negative 3 over root 2. And we have negative 3 over root 2, and a positive 3 over root 2. Those are 2 points that we get on the boundary that are possible maximum or minimums. And they're the only points. We don't run into any other points on the boundary that would be the same. These 2 points are actually the point here and the point here. we need to go ahead and plug those into our function. We're going to take x and y at those values. We're going to go ahead and plug those into the function f of xy, which is, remember, that's x squared plus y squared minus 4x, plus 4x minus 4y. And I'm just going to kind of put those in for you. You can use a calculator for this part if you want to, but just recall the 3 points that we've gotten so far. This first one is, well, the first one's actually pretty easy. This is going to be a negative 8, because we get 4, 4, minus 8, and another minus 8. The other two, we're going to end up with keeping the square root of 2's because of the x and the y that are by themselves here. These the squares actually kind of got rid of them. But for the first one, we get a 9 plus 12 square root 2. And this is approximately 25.97. The other one is 9 minus 12 square root 2. And this is approximately negative 7.9, negative 7.97. So, kind of want to be able to compare these values. So, 9 minus 12 square root 2 compared to negative 8 would have been kind of tricky. But if you write it out in decimals, it's clear that while they are really close, negative 8 is actually smaller. So our absolute minimum is negative 8 at the point negative 1, 2. Our absolute maximum, there, why did I put it there? The absolute maximum is the 25.97. At the point 3 over square root 2, negative 3 over square root 2. We could go ahead and graph this just to get an idea of what's going on. I'll start with graphing my function f. So let's go ahead and call it f. Plus 4x minus 4y. We get this thing. Let's zoom out a little bit so we can actually see that it is. It's a paraboloid. We go ahead and plot our constraint, x squared plus y squared equals 9. It's going to plot it as a cylinder, and that's actually works to our benefit. I'm going to go ahead and recolor that, make it stand out a little bit differently. So we're looking at all the values of our function that are inside of that cylinder. So if we were just kind of look downwards on our cylinder, it's kind of all the values that are inside there. A little hard to see what's going on here. But you can kind of tell that of all the values on the paraboloid that are inside the cylinder, it gets to a high point up here, at this point up here. And that's what we should expect. That is our point of 3 over square root 2, negative 3 over square root 2, and then the y value, the z value there, the value when we plug it into the function was 9 plus 12 square root 2. And that gives us a point, which they labeled A, that's at the very tip top of that thing. If we were to plot the corresponding point, the negative 3 square root 2, 3 square root 2, and then 9 minus 12 square root 2. And what did I do wrong? Oh, I did the same thing I did wrong earlier. These are supposed to be 3 over square root 2's. Okay, so we get a point way down here. It looks like it should be at the bottom of what we have, but if you zoom in a bunch, and let's move this up so it doesn't go off, you can tell that the paraboloid actually bottoms out at a point that's slightly inside. That is the point that we identified of negative 2, 2, then z value of negative 8. And is inside there, so we can't really see it very well. Can we? Oh, there we can see it a little better there. So the point C here is the absolute minimum that we found, that is just slightly inside the circle. But you can see that it's because the vertex of this paraboloid, and it actually ended up inside of the actual constraint here. It's inside that region, even if it is just barely inside. And so while you can definitely tell that this other point, this point B, is a minimum for our function on the boundary, it's not a minimum for the overall thing. And that's really all that came down to it. There was a lower point on the interior to replace it as minimum. So hopefully you can kind of see how the process goes, even if there's a lot of ambiguity about how we might solve the actual systems of equations. That's not the easiest thing in the world, and it generally is what will trip up most people. You just have to keep playing around with it. If you have any questions about actually solving a particular one, feel free to ask me about them. That's all I really can say here. I can't give you any more general techniques than maybe try eliminating parameters, or try and set things equal to 0, and discuss different cases. All those kind of things that you saw me do here are going to be useful. But I'm going to leave it off here. And keep in mind, our first exam is coming up next week. Make sure you try out the problems with this. Make sure you see if you run into any issues before that exam. And if you have any issues, please let me know. Send me an email, or you can also attend my office hours. I do have my office hours on. My next one is on Tuesday at 1 to 2. It'll be before the first set of exams. If you're taking the exam on Thursday instead, I will have another office hour on Thursday at the same time. If those times do not work for you, or you need additional practice, try contacting me. We could possibly set up another time to meet, but you'll have to give me time to actually make sure I have time available for that. So I don't know. I haven't seen a lot of you in office hours, so I don't know exactly where everybody is standing on this stuff. I'm kind of curious about whether or not you guys are actually staying up to date on all this stuff. But I'm going to go ahead and leave off this video. I'll see you guys at the first exam.